I'd like to introduce Professor Marco Lavorato from UCI. He's going to talk to us about dynamic and distributed computing for autonomous vehicles. Thank you very much for joining us today.
I look very young. That was like a pre-tenure picture, unfortunately. Now I'm full professor, or like you can see it. So I'm going to summarize a little bit of the research that we have done in the area of distributed computing for real-time systems, especially over unreliable infrastructures, like a wireless infrastructure. I'm going to tell you in a minute what these are. A little bit, just very quickly about me. So actually, I got my PhD some time ago from Italy, from University of Padova. It's actually the second oldest universities in the Western world. We still have the desk of Galileo Galilei, his office. He was a faculty there. And then, Italy is a wonderful place, but I decided to move to the US. And I moved in 2010 as a postdoc at Stanford and USC. I didn't know much about these universities. Actually, I remember my wife asking me, but is Stanford like a good university? And I say, well, I think it's okay. I think it's okay. But, and then she moved there she joined the PhD program there, we moved to the US permanently. And then 11 years ago, I became a faculty at UCI in the computer science department, even if by training, I'm actually an electrical engineer. So I studied telecommunication engineering. And then you see there is a little bit of a mixture of the two in the talk. And so a little bit of systems, a little bit of AI. We do a little bit of everything. At UCI, I lead the Intelligent and Autonomous System Lab. This is a LiDAR scan of my group. You cannot see the face, but we need to have a little fun with all the equipment, all the things that we have. So this is actually like how you see like autonomous cars like driving around, perceiving the world through these sensors. This is how they see us. You can still see this is a master student doing this like that. He's very positive and. So you can see some of the details. Okay, so we work on many different applications, on many different systems. I'm summarizing here some. Most of what we do is connected eventually to computing needs, to systems that need to analyze the environment, make decisions. And this applies to many different systems: autonomous cars, autonomous drones, collaborative robotics, manufacturing, mobile healthcare. These are all augmented reality up to some degree. All systems where you have essentially mobile devices that acquire data from the environment. They need to analyze them, sometimes make navigation decisions or decision about what to do or discard a piece of something, or in any case, complex decisions. And the problem typically is that this kind of analysis is very complex. Right? We need to analyze a lot of data. The algorithms are complex, while all these mobile devices have constrained resources. And I'll tell you a little bit about this. But of course, you can imagine that an airborne small drone has limited computing power, has limited battery, has weight constraints. So there are a lot of this that happen. And so I'll tell you a little bit about our solutions to this kind of problem. And our group has been funded by the defense. A lot of what we are going to see today actually relates to some defense applications. We had a lot of projects, of course, with National Science Foundations and some industry, Intel and Cisco. Now we have more heavily invested in autonomous vehicles. We are starting to collaborate with Boeing and with some other companies. This is a very complex problem, like how you build computing systems that can solve this type of challenges. And it's a very complex problem that has many different components. And we try to tackle all of them. It's not easy, but I think they are so strongly connected that it's hard to solve the whole problem if you don't address all of them. So I'll show mostly today what we do in terms of AI algorithms, how we reshape AI algorithms to account for the fact that we have limited resources, that we have distributed systems that need to handle these kind of things, how we reshape intelligence, okay, from this point of view. But we do have work on different parts of the system. For instance, how individual devices make decisions about how to compute. Should I compute? Should I transfer the computing task to something else? And this is a typical 5G kind of problem where the infrastructure has computing capabilities and can take over portions of the computing effort. Okay? But there are other more infrastructure level problems. For instance, how much resources I allocate to this kind of cluster of applications, or how I handle the whole mobile to wireless to computing pipeline. Okay, so we try to tackle all these problems, and one influence the others. For instance, when we introduce new algorithms, they tend to change the way the workload that the infrastructure needs to handle, right? And so we try to build logics that also deal with that problem. Okay, it's very interesting life, right? We do a lot. Like I wouldn't say I'm, an AI kind of guy. I saw two of my colleagues coming, I think this year. Samir, he's more like large language model, like Core AI. Faisal, he's more data center system kind of guy. I'm in between. Like I try to solve this kind of problems. So let's focus on one of these applications. And tonight I wanted to talk more about autonomy and autonomous decision making. And I'm going to focus on vehicles that need to navigate the environment and the kind of decisions that they need to make, and the kind of modifications to traditional paradigm that we make. So when you think about a pipeline for a stack for autonomy, for instance, for an autonomous vehicle, it's a fairly complex modular kind of suite of composition of algorithms, right? For instance, you see here first layer of perception, right? So the data that are collected from LiDAR, from images, you need to process them to extract objects, to segment the road in front of you, to detect lines, to detect the lanes, detect the portion of a road where you can drive, and all these things. And of course, also classification, where you classify, I don't know, a traffic sign or something, or a pedestrian rather than another object, right? So this is a first layer of computer vision algorithms. And then there is another layer of algorithms that take the outcome of a first layer and is dealing with semantic extraction, for instance, reasoning, essentially. So can we associate a traffic sign with a specific lane? How do we know how to turn left, right? These are sort of very high level reasoning that is based on the perception, but is more complex from a reasoning perspective. Then there are other modules like motion and prediction, mapping and localization, path planning, vehicle, and eventually the control, right? So all the control layer. Where I want to go, how I'm going to do it, right? So this is super complex, right? If you think about what's happening in autonomous cars, this is the kind of pipeline that you see, even if some solutions that are emerging now take this whole thing and crunch it into one monolithic algorithm with all that comes with it. But the problem is that this whole thing requires a lot of computing power. And when you look at what autonomous car looks like, the trunk is not going to carry your luggage. It's carrying GPUs, right? And this is costing a lot more than the car itself. It's costing a lot of energy to the car. So the power that this kind of boxes here is drawing to support all this computing is a big portion of the overall consumption of a vehicle, right? And this is the problem, right? One of the problems. Of course, there are other vehicles that are being developed that are capable of autonomy. Of course, this is a Boeing vehicle. When I started interacting with Boeing, I told them, I work with drones, and my drones are hexacopters, quadcopters. And my friend from Boeing told me, yeah, we have drones too. And I said, well, I don't think your drones are like my drones. Like, I don't think we have the same problem. Like, it's not like a fighter jet, like in my office. It's like little smaller things. But this, of course, doesn't have a lot of constraints in terms of cost, in terms of, power, right? And by the way, airborne and ground autonomy are fairly different in terms of complexity. It's actually fascinating to think about the fact that flying an airplane is semantically easier than piloting a car in a complex urban environment, right? All the reasoning that comes with it, all the things that come with it, is a problem. It's a different problem. Now, where I come into play is when you want to put all of this into devices that are a lot more constrained compared to a car or compared to like a huge fighter jet, right? Let's say you want to have a micro drone that is scouting an environment, identifying objects in a certain area, and is reporting back. Okay, can we do this autonomously? And that's the problem is, okay, that object there has a very tiny battery, maybe has a tiny, tiny GPU, maybe not, maybe it doesn't have a GPU even, right? So how can we take that object and make it autonomous? Okay. Same for maybe larger drones, still like less maybe extreme from that point of view. You see also these delivery vehicles, they are, of course, they don't have all the complexity of a car driving in a street, but they have much more constrained hardware, much more constrained resources. So how can we build logics that support this kind of autonomy is still like a huge challenge, right? And not even just navigation and reasoning, but even perception is hard. So even if you want to take a CubeSat and put AI on it, then you have a problem of this object being solar powered, of having a small battery, of having a small GPU. How are we going to put AI on those kind of objects, right? Just to understand the environment, detect a ship, detect something that is happening on the surface. But even traffic or city monitoring is hard. And I was fairly surprised by this. We had some interaction with the city of Irvine. And it was very funny to see that they are expanding their monitoring hardware to include not only cameras, but also LiDAR. And that the specific reason of this is that they want to be resilient against illumination conditions, adverse weather conditions. If you shoot a laser beam and you get back, many laser beams sequentially, as in a LiDAR, of course, you're less sensitive to some weather conditions or illumination conditions. The problem is that you generate a lot of data, and you cannot really process effectively LiDAR on board a camera. You need to transfer the data somewhere else, and that's a lot of data. So Irvine tried with 5G, AT&T failed, and then they had to deploy optic fiber and move the data with optic fiber. So it's hard. I mean, it seems, we are used to hear about AI taking over the world and large language models that reason and all these things, but all these things happen on the cloud. And that is using a lot of resources, but they have it, right? When we move to the mobile domain or to the small device domain, things are a lot harder. And I know that NVIDIA, I hope there's nobody from NVIDIA, but NVIDIA is telling you the opposite of this, that they can put whatever you want on their GPUs. It's not true. I mean, it's too much power, it's too much load. You can run object detection really fast on one GPU using a small model, and you can do it, but object detection is not an application, right? It's not doing much more than that. Okay? So I hope I convinced you that this is a difficult problem. I'm going to tell you about the vision of what we do and some pieces of it. So we want to build systems of AI systems here that are capable to, first of all, distribute the algorithms over multiple devices, multiple assets. And you can think of this as the drone having a ground support vehicle, the camera having a data center in the city, all these kind of things where you have an asymmetric setting. Even in the CubeSat example, the way CubeSats are launched now or are thought, the vision about CubeSats is to have heterogeneous constellations where you have some CubeSats that are mostly for sensing and one big CubeSat that is more for computing. So this kind of distributed systems, asymmetric systems, are emerging in so many different areas and so many different applications. The problem is, how do we build AI systems that can operate efficiently in these kind of systems, right? And the way we do this is by building sort of new algorithms that are capable of being partitioned into multiple sections and minimizing the amount of data that is transferred, and also making them adaptive. And I'm going to explain this in one second. But the logic of it is that typically, when you train or you design a machine learning algorithm, you design it for the worst case, right? You have a huge computer vision algorithm, and then your camera is staring at a blank wall, and you are using a lot of power to just say it's a blank wall. And that's very easy, right? So the algorithm should be able to adapt and be able to say, no, it's a very simple problem. I shouldn't be using so much computing power to just give you this answer. And we do this all the time with our brain. When you are performing a very simple task that you're trained to do, you don't use your full computing power. You just do it until something happens, and you reinflate your attention and your power, and then you analyze more. So this is the kind of logics that we build. And the idea is to have algorithms that are modular, that are adaptive, that are partitioned into multiple sections, and that are distributed. And then you have mobile devices on one side, your little drone, your little Mars rover, whatever it is. And then you have the bigger motherships that are taking most of the load, if you can, if a wireless channel is good enough to transfer portions of the data. And you have little agents that are operating, analyzing the data, analyzing the system capabilities, and they reconfigure this automatically, right? So this is the idea. In the end, the whole thing is going to look something like this, where you have this kind of adaptive branches, what we call like lightweight swarm intelligence, where you have algorithms that automatically inflate or deflate their complexity. If they can, they transfer compressed version of the data to some bigger device. And then here you have multitask adaptive algorithms that, for instance, in this case, this is a navigation setup. Then you have to support 3D mapping and localization. You need to support object detection, segmentation, all these things. But the complexity of this changes in response to the context where you operate, in response to the specific task you are performing now. It needs to change in response to the state of a wireless link, to the energy that the different devices have. So the question is, can we build algorithms that can do all of this? That if I have a small amount of, like my battery reservoir is almost depleted, can I simplify the algorithm automatically? And I need to load another complete software, right? So this is the vision. I'm gonna, a lot of what, I know I'm an academic, so my business is ideas and papers, right? That's what we sell, right? But what we do is really, we try to ground it on actual systems. So we do have, I do have my fleet of drones. Some of them are crashed, and some of the big ones just crash. Like students, do a lot of damage to think, like we are not like a big company. I remember at some point we had a project with DARPA, with defense, and we were using drones from the defense, and my students wrote the wrong piece of code, and the drone just crashed on the wall. And I say, oh, I'm sorry, Tom. I'm sorry. No. That research is so exciting. I say, okay, we can crash more, like if you like. It's not a problem. But we have a fleet that is composed of micro drones, quadcopters, autonomous rovers, all the sensors. We do build real systems in the end, and a lot of what you see is actually tested on actual systems, and we try to build. You see some of our rovers. Of course, they don't look as pretty as those that you see in the companies, but we have binocular cameras, planar lidar. We test with different radio interfaces. We have all the NVIDIA, possible embedded computers that you can think of. We test with so many different things, and also radio system, of course. So this is the idea. So if we are all on board, and I sold you the need for these kind of things, I just want to sell more, like a little more, actually, and that, like try to make you understand what this problem looks like a little deeper, okay? So if we go one layer more specific, so this kind of problem, you simplify a little bit. And you say, OK, now you have an airborne device, for instance. You are acquiring image and LiDAR information. They are acquiring, this is being acquired continuously. So you acquire, for instance, 15 images per second, right? 2 LiDAR scans per second, right? And these correspond to a stream of tasks that flows through the system, and then you need to apply all your algorithms on this task, like object detection, segmentation, classification, so on and so forth. And in some cases, this turns out to be a control problem. Okay? Not in all of applications, but in some applications, right? So this is the problem. So what industry and even academia up to some time ago was trying to do was actually to, OK, we take the algorithms, the neural network, and we simplify it. OK, so now my neural network is smaller and is trained, for instance, to mimic a bigger neural network, or we quantize the weights, or we do things that we make this a little simpler. Like there are many different ways of compressing the models: quantization, distillation, pruning, whatever you want. Okay, and they work well, right? That's the way it's done. But there is a problem. First of all, you need to support the algorithm, and that's hardware cost. So if you want a GPU that is executing object detection 20 frames per second, it's not a non-negligible cost. Okay, things are slowly changing, but that's the idea. Then there is task performance. When you compress these algorithms, you tend to lose performance. Okay, no matter what you do, a small model is going to have a perceivably smaller performance compared to a state-of-the-art large model. So you have a trade-off between performance and latency and energy consumption and all the things all the other performance metrics. Okay. Then energy is one of the biggest concerns in many of these systems because they are mobile. And if I don't show the specific numbers here, but if you take an NVIDIA Jetson Nano, you run object detection at 20 frames per second, your power consumption goes from 2 watts to 8. And that's 25% energy that is used to fly of a quadcopter. Okay, so it's non-negligible amount of energy. And then you're actually doing only object detection, again, which is not what you want to have on the drone. Right? There's another aspect that is not maybe considered as much and was new to me up to some couple of years ago. It's hardware degradation. If you have a GPU and you run it full-blown for 2 years, it's not going to last like very, very long, right? And then you have to go up on the traffic, on the top of a building and change the GPU, and that is a cost, but it's a cost even just to go there and change it, right? So, unlimited functionalities, again, of course, you cannot put too much stuff in one small GPU, right? So the other paradigm that emerged at some point, especially with 5G, that's why I refer to 5G, is essentially what is called edge computing, right? Which is, I guess you're all familiar with cloud computing. Edge computing is a version of that where the server is much closer to the wireless edge of the infrastructure. So you reduce latency. You have to go just to a couple of hops in the core of a network. You don't need to go all the way to Finland, right? So that's one idea. And so the mobile device will send the data over the wireless channel. The edge server will do all the computing, and you get back control. Everybody thought this was going to work wonderfully. Like when I started this, I got a lot of pushback from academia, from industry, because everybody said, 5G is going to solve the problem. You're just going to transfer the data through 5G. We're going to be fine. And then 3 years after, I got all the phone calls from Verizon, AT&T, T-Mobile, Deutsche Telekom. And I had this wonderful moment when the Deutsche Telekom guy told me, edge computing on 5G doesn't work. And I said, I told you, that's why I was working at the time on this problem. And it's not that it doesn't work, it's that it's not financially viable because you need to have too much resources dedicated to every application, like too much bandwidth. Bandwidth is expensive. So the problem in general is that wireless I'm a telecommunication engineer. Wireless channels tend to be hostile and volatile. even 5G channels, even, they tend to be constrained in capacity. They tend to be time varying. You cannot really rely on them if you are supporting a mission critical application, right? And you see this. These are some measurements that we took. This is, they can tell you, okay, you have a lot of capacity on average, right? But then when you look at fine grain, this is the time to transfer an image over, some outdoor with building environment, and this is the delay. And you see that, well, depending on some parameters here, you have spikes and erratic behavior. So you cannot read, and this is a good, Wi-Fi system. Is .11ac, is a multi-user, for those who knows, is a multi-user MIMO with parallel stream. Here we're using maybe 4 antennas. It's a fairly strong Wi-Fi system. So you have uncertainty. That's not going to go away no matter what you do. You have bandwidth usage. Companies are not happy if you use 50% of your bandwidth to support one application and they paid like 10 billions for it, right? And you're sharing with other users and services, right? And that is a load that changes over time too. And then still hardware degradation up to some degree of the edge computers. Edge servers are not cloud data centers. They are maybe more resilient, but still they are much smaller in many cases. It's just maybe small server attached to a base station, right? So it's a different system. So that's the idea. So this is not a solution either. So we started working on this, and we started from the point of view, can we reduce the amount of data that is transferred over the wireless while reducing computing, while minimizing computing on the mobile device? And that's what I refer to as distributed AI. So of course, you're not if you're transporting images, for instance, you're not transmitting the raw image. The first thing you can do is JPEG, right, or MPEG. The problem is that those kind of compression are designed for human consumption, not for machine consumption. When you compress too much with JPEG, you see blurry edges, and most of what a computer vision algorithm does is detecting edges, so you are losing that, right? So when you compress too much, JPEG and MPEG have like very, very bad performances. Or you can use like one of those fancy large neural encoders that, I don't know if you're familiar with it, there are many like large encoders for video, for images. They tend to be extremely complex, more complex than the object detection algorithm or the planning algorithm or whatever you have. And they have high performance, but they tend to use a lot of this compression power to recover the full image. And to be honest, to perform a specific task, you don't need the full image. For instance, think about you're trying to detect pedestrians, okay, and you have a general image. A lot of the details of the image are irrelevant. Like all the details of the foliage or the leaves or the trees, all these things are not relevant. You can remove them like very easily, right? And so these kind of algorithms are not designed for that. So what we did instead, and this is what we became most visible for quite some time ago, is actually try to build a new compression paradigm that would essentially take a supervised approach in a way. And I'm going to explain this in one moment. We refer to this as split deep neural network. There are some friends who joke and say I'm the king of split because that, our group invented this kind of approach. The idea is that, so let's think about this. You take a deep neural network for computer vision. One thing, you want to distribute it over multiple devices. You can just cut one of the layers, and then you execute this portion. We call it the head model on the mobile device. You execute the tail model on the server. Okay? This was the first version of it. There is a fantastic paper called Neurosurgeon that does exactly this. It's a very high citation. It's very funny that it shows that this doesn't work. And the problem is that these kind of algorithms are not designed for compression, and actually the first layers tend to expand the input and actually have, if you cut it here, you transport more data than the input. And you're actually, unless you go toward the end here, but then you are executing most of the algorithm on the mobile device, and that defies the purpose. Why should I make the effort if I've done most of it? So that doesn't work. What we have done is actually try to modify this architecture. So we take the original architecture and we modify the architecture and the training so that we create essentially a compression point. You can think of this as a form of compression that is designed inside the model. So it's, as I execute the model, I also compress the data, and then I re-expand them. And this is, we call this a bottleneck. So the whole trick is about designing these kind of models that very early in the model squeeze all the semantic meaning that you need to perform the task, and then transmit very small amount of data with limited effort. Okay? This is what we do. If you look at this from like a functional point of view, what we are doing is actually building a supervised compression algorithm within the model. So you can think of this as an encoder, and then a decoder and classifier. But the encoder is part of a model itself. Okay? And we call this supervised compression. And it's different from compression because you are essentially building this model to perform a task, not for the recovery of the input. This is what makes this effective. Okay? So I can tell you like how it works. It's actually very, very interesting. But it requires a little bit more background in terms of what happens here. Essentially, what we are doing is training that first part, encoder and decoder, to mimic that same portion of the original model. So we are not training encoder, decoder to recover the input. We are training that encoder, decoder to mimic the original model. Okay? And then there is some complex training here that goes on, and multi-phase, multi-stage training, and we build our models. Okay? We have some more sophisticated version of this. I'm not going to cover them. What I'm going to show is that this actually works really beautifully. And you need to think about this from a three-way trade-off. And performance of a model, in this case accuracy, is image classification, the size of the data that you transmit, and the encoder size, so how big the model is that you execute at mobile device. These are all state-of-the-art algorithms in terms of neural encoding. And the blue is our own. And you can see that, first of all, we are on this side of the plot. So we design algorithms that are extremely simple. Not only that, but if you look at this curve, it's very high, which means that we are actually providing a very good performance, final performance of a task, even if we transmit a very tiny amount of data. And in some of the versions of this, we can take a 800 kilobyte image, high resolution image, and we squeeze it to 8 kilobyte for object detection. Or if we are supporting navigation, we can squeeze it to 1 kilobyte, and then we transmit it, and we support this specific task. If you look at the way the model focuses on different parts of an image, so here, again, I'm not going to talk too much about this, but if you look at this, where you see red is where the model is spending the most representation compared to a state-of-the-art neural encoder. And you see that we focus on the objects. We lose all the details of the fine detail of a lawn there. We lose a lot of tiny details that would, you see that, I don't have it here, but there are some interesting examples. But you see that we focus on the task at hand, which means that the model is focusing its own power, its own representation to a specific task. So we have models that are trained for computer vision tasks, that are traditional image detection, that are semantic segmentation, object detection, and they're extremely effective. But now we are moving into the domain of autonomy, and that's where some of even more extreme gains can happen, actually. I'm going to show some other plots. So here is a power consumption curve, like distribution compared to edge computing and executing like locally some some compressed models, we have a lot less effort. We have a lot less effort compared to even a compressed model. And we provide like a lot more, more performance. Now, this is, of course, one component, like one building block to me of a full solution. There is a lot more to be done. For instance, we explore some other solutions where, for instance, if you have enough computing power but you focus on energy, then you can build actually, like use this kind of logic to build multi-branch models where you have, if a wireless channel is not as good as you want and you cannot transfer data effectively, you fall back to local version of this, and you have a small decision-making module that is even selecting how complex the algorithm should be. This was done specifically to transition from images to control of a simple control problem of an autonomous car. Okay? And we showed that you can actually automatically design this kind of models. You can build compression points. You can reduce energy, and all these things. Okay. Now, the problem, again, a little more complex problem comes when you think about navigation, right, itself, rather than just like simple control or simple computer vision in a way. So we started looking into the planning of a path itself. So we consider a simple drone setting where you have just a simple camera, and you want to navigate the drone in a 3D environment from one point to another. You have GPS. The drone will need to autonomously navigate in the environment just based on the images. Now, and the input is just GPS and RGB image, so very poor sensor. So we're looking at micro drone here, essentially. How do you do this? Well, the first thing you need to do is actually to take this image and estimate depth. For navigation, you need to know how far away the objects are in the environment. So you decide how to plan your path and avoid them. And then the modules that follow this is a navigation logic that takes the depth map and decides where the drone should go. Okay? The problem is that while we are in a micro drone setting, so the problem is still complex because the depth model, the depth estimation model that takes an image and tells you how far objects are, is still a complex neural network. You can compare this, if you're familiar with this, to semantic segmentation in a way. So this part of a model is fairly complex, even if this is not. It tends to be like a lot lighter weight. So how do we do it? Well, we used the same logic, and we say, OK, now we split the compression. We split the model into two parts, and we create our compression point. Okay? And we see how it works. But this is a specialized problem because it's a control problem. And if you think about the environment that the device needs to operate in, there is a lot of different environments, right? The drone could be flying in the open sky, with GPS, no objects around it, and then the problem has a very low complexity. If you're operating in a complex environment with many objects, then you have a lot more complex problem, right? So this actually reflects on how much data you need to transfer. If I am in a very simple environment, I don't need much information. If I am in a high complexity environment, I need a lot more information, right? So we build a system which is, I think, like very innovative. We presented this. Well, we haven't really presented it yet. It's accepted but not presented yet. And it's a self-adaptive form of neural network. The idea is that now the model itself is modular, and we can pick the specific kind of compression, the specific pair of encoder, decoder, and tail that perform image to depth pipeline based on the environment. So we have this feedback loop based on this auxiliary model, which takes the control problem and decides how to represent the data. But we got some really interesting results. Actually, if you look at what the model is learning over time, and by the way, training this kind of model is a nightmare. You need to use deep reinforcement learning, curriculum learning, knowledge distillation, quantization, slimmable neural network. It's fairly complex architecture, but it's really functional. And what we see is actually that as the drone is navigating, the complexity of the representation will change. And it's really interesting to see that the highest complexity is actually when the objects are not too close and not too far. And that's actually fairly reasonable if you think about this, because if the objects are very far, then there's not much you need to do. If the objects are very close, the decision is fairly obvious. Like you just fly, try to avoid it. So there's not much complexity about it. But when you have mid-range objects, then you need to decide how to navigate, and that's where we need resolution. So that's the idea. And we show that this is better than JPEG, this is better than many other things. But what really amazed me is that we can go to depth, like a good depth representation, transmitting 1 kilobyte. And this is a very tiny, we take a high resolution image, but what the controller will need is on this line here if you compress for the task. Okay? And so this is really interesting. Of course, for, if you look at 5G system, transmitting 1 kilobyte doesn't make a lot of sense. It's a small payload. But if you think about a micro drone operating in an unknown environment, then actually being able to transmit like a small payload is very critical. From a point of view of latency, from a point of view of load on the channel, but even from a point of view of being able to avoid jamming, to avoid other problems that different agencies care about. So this is one of the solutions, and actually, so we have these plots where you see the different choice of the algorithm based on the map, on the environment. It's actually very interesting to see where we focus more of this. Okay, I'm gonna show you, but the problem is what I show you is a technique which is still, so it's one aspect of a problem. Like think about what we are doing here. You have two extreme points. You have one point where you are sending all the data to a server. You have one point where you are executing a smaller model yourself. These are extreme points, and they are optimal in their own parameter regions, right? I have a good server, I have a good channel, I can offload. There is no problem. If I have a very bad channel, I will need to execute everything myself. What I'm offering here is another operating point. So it's something that can support this computing pipeline in between the two extreme points. So we are expanding the operating point. But I'm not saying that split computing technologies are always optimal. And so the problem is, how do you dynamically adapt this kind of pipelines like in real time without actually the need to rebuilding your pipeline every time? So what we did, and this is actually showing where different compressions or options are optimal depending on the signal strength, on the number of clients. This is still .11 AC, so a good Wi-Fi protocol. You see that sometime when you have very good channel, you can go into like JPEG. That's not a problem, right? If you have a bad channel, like really bad channel, you have a lot of other users competing, then even split computing cannot make it. This is actually for an object detection pipeline. So you transmit a little more data compared to navigation. So the problem is, how do I dynamically activate, deactivate different portions of this pipeline, and how actually something that we have seen and we haven't fully explored yet, which is how do I make this algorithm specific to the operating context in a way, for instance, that is, if it is raining, if you have snow, fog, I can train encoders and models that are specialized to that environment and that perform a lot better than a general algorithm. And so the problem is, how do we reconfigure this? And what we did is actually build a containerized, modular kind of approach where we essentially embed the AI algorithms into lightweight containers that are activated, deactivated dynamically based on the context. And actually was an amazing result. I'm not going to show much about this, but everything that we build is compatible with NVIDIA API, is a fully functional way of reshuffling this kind of computing pipelines across different devices. And we built a logging agent which is looking at what's happening in the system and decides what to do. Okay? Just to mention this. Okay? Not going to talk much about this. But there is another frontier of this kind of algorithms that I want to mention and that I find is really interesting. So again, you are all familiar, I guess, with AI algorithms that are static in a way. Right? I take an input, it goes through a series of transformations, and then I get an output. As I said, that tends to be designed for the worst case. Right? If I have a very complex urban setting with a lot of objects, a lot of things to detect, to analyze, or I have a blank wall, but still goes through the same algorithm. Right? That doesn't make a lot of sense. But still, given that I don't know what I'm going to encounter, the designers tend to optimize for worst case. Right? And that's the problem. There are some versions of neural networks that are actually they're called early exit. So they have some branches that are activated if the inputs are simple enough. So the network becomes shorter. But there is a relatively new class of models that are actually very interesting, that are capable of adapting their width. Okay, so they call them slimmable neural networks. So the model is actually composed of slices, and the model itself will be capable of understanding how many slices are activated. Okay, so the area is still largely unexplored, and most of what you see for these models are actually still static models that you can change depending on what applications you have. But what we built is actually a version of these slimmable networks that can self-adapt. So we change the size of the algorithm, of the complexity of the algorithm at runtime, completely seamlessly, and in a self-aware way. And that, I think, is the cutest result that we had recently after split computing. The idea, I'm not going to talk about this, but you can think of this as having a super network that is the most complex version of the algorithm that you have. And then you train essentially a set of what we call subnetworks, which are obtained by removing some of the nodes for every layer, creating these slices. And then you train this in a specialized way, like as an ensemble set of algorithms using knowledge distillation, using many of this algorithm. Okay, so we built an architecture for navigation that I find really interesting, and it's mostly focused on that. When I show you, the earlier navigation framework, I was assuming you have an RGB image, you process, you extract depth, and then you have a navigation model. In some settings, so here we are focusing on a setting where you actually have multiple sensors, like LiDARs, that are acquiring directly depth maps. Okay, you have a forward sensor, which is giving you a depth map. You have a downward sensor, which is giving you a depth map. And then we have these algorithms, which is this slimmable neural network, still with a tiny auxiliary model, which is analyzing the output, the control that is happening, some crunch version of the images, and it's producing slimming factor, so how complex the network should be. Okay, and actually, the different slices, again, it's a little more technical here, but the different slices will be attached to different sensors, and the algorithm will automatically select which sensor to activate. When you see it, it's actually very beautiful in a way that the algorithm is dynamically deciding, I'm going to look more specifically forward, I'm going to look more specifically downward, I need to look at both, right? And actually, so we are building versions of these algorithms that have depth estimation, that have different sensors, and have full navigation capabilities. And again, actually, we got the same result. Again, when you see these maps where you look at which sensor you activate and the complexity, you still see the same logic that is learned by the algorithm. The biggest complexity is activated when you have objects that are in mid-range. When you have objects that are very close or very far away, you use the smallest complexity because you just need to. Either you need to do nothing and just follow GPS, or you need to avoid the object. And we saw the same thing, and we got really excited because now we can match the two sections and use for the navigation, for the depth. We can connect different slices to LiDAR, so we can move toward a full vision. We have some version of this that are more complex. I'm not going to talk too much about this. So the vision in the end is to build this kind of systems. Like that's, like my kind of dream is actually to build look at the whole system as a unitary intelligence, right? Where you have different assets that will have different slimmable compression heads. You have assets that are capable of computing and will need to activations of their tail models to extract different meaning from the data, right? And again, I'm showing what these things are. And you see here, our slimmable heads that are taking an input image and sending it to the centralized intelligence. But the beauty of this is that you can perceive, well, here we have slices that are connected to multiple sensors. All of this is very, when you get how this thing works, all of this is very simple. And then we can tune the representation to the specific task that you are performing in that moment. And might be 3D mapping if you need it. You don't always need 3D mapping. Like if you're flying the blue sky, you don't need to 3D map the environment. You need it if you're flying under the tree canopy, for instance. The compression for that, if you need to run object detection, you need a little more data every now and then. If you're running segmentation, you need a little bit more, again, but not all the time. And you can think of the different slices of the models that are. There's a C here. I think it's maybe it's cool, but I don't know. I hope so, but it might be. But okay. So this is the overall vision. A little bit about this is, I think it's we are using the very simple, simple version of what we can have on this kind of devices, just because we are used to think about this kind of algorithms in a certain way. And, making them dynamic, making them distributed gives you a very strategic edge, as you can actually activate more complex functions somewhere else while having full functionalities on mobile devices. You can tune the complexity, you can maximize battery lifetime, you can minimize channel usage. And again, no matter what system you consider, wireless systems are really volatile and uncertain. So you need to tune, and you share with the mirror might be hostile, no matter what. They are, other devices, and you cannot just assume you can send the data. But if you just limit yourself to compute on board, you're gonna have very, very simple AI. When people show me like fully autonomous drones, like micro drones, I always think, I don't know, like it doesn't sound like really. We went to visit a company, I'm not gonna tell the name, like it was a group of faculty, and they show like this swarm full autonomy reasoning and system, and we look at each other with other faculty work, and we say like, this is not the whole system and you leverage the resources of a full system, then you can actually build this kind of logic. So I guess just when, given that I have time, and you can blame him for this, I want to show you one more little piece of this, which is the focus on communications, right? And as I said, like we work on many different aspects of this. When like everything that I've done is sort of oblivious to the specific communication system that you use. I just say you can or you cannot. That reflects the data rate that you have reflects on the configuration of a model, but that's it. I'm assuming you transport the data the same way you have always done, right? But that's not necessarily the truth, and there are new ways of thinking that are emerging in terms of communications that actually are aware of the data. We call them when you look at the state of the art, what people do, have always been doing communication systems, is actually just to look at communications systems and resource allocation just based on traffic, right? For instance, I need to transport 10 video streams, right? And that was those 10 like each video stream has 4 megabit per second, and then I need this much bandwidth, right? And then the video streams oscillate over time, and but that's the kind I still assume like the worst case setting where I allocate the maximum bandwidth. But there is an opportunity, and the opportunity is actually to tune the communication operations and the infrastructure level operations to the type of data that you're sending, right? For instance, what I show you is a kind of dynamic model that are going to adapt. So the infrastructure could reason in terms of, oh, I have some users that are pushing in using more and more resources, then I can actually push my model to deploy more and more computing load locally and compress more and more, right? That becomes an interplay between what happens at the mobile device and at the infrastructure. But there is another problem, and it's that when you allocate resources in these kind of systems, often you think about average, right? Well, here we need to contorting are not just general data, are sequences of images that need to be processed for control. Okay, so you need to avoid these spikes, right? You need to transport. You have a deadline, and you need to transport the packet by that deadline. So the idea is that you can build communication systems that are aware of a task. For instance, if I transport an image, and it's not a movie, it's not an Avenger movie where I want like 4K, full-blown definition to enjoy the movie. This is a system that can actually deal with maybe lower resolution, but that depends on the task. If I'm just trying to detect a traffic sign, or I'm trying to segment semantically an image, those are two different tasks that require different amount of data, but also different reliability of a communication. I can also operate based on the context, right? I can embed the need of the algorithm based on the operational context. But I can also tune my logic, my communications, fine-grained spikes, right? And this is what I'm going to show you very briefly in 1 minute, is that if I'm aware of this, I can try to predict the spikes and change my communication system to actually match the needs, specific needs of a task. Okay? So this is something that we have done fully experimentally. So we took our rovers, we left them alone, navigating somewhere on campus without telling anybody, so don't tell UCI. But these at least are ground robots, are not, we have this thing that at some point we were testing with huge hexacopters with large propellers, and those can like chop the head of an undergrad student very easily, and so we were a little more cautious with those, but these are ground robots. So we tested in some open environment, we tested in actually like more obstructed environment, indoor environment. And in the end, what we built, let me show you just very briefly this, is that you can actually build a whole communication system that is aware of these spikes, is aware of the characteristics of a task, and is controlling the communication configuration. In this case, again, if you know about how this kind of system work, we are controlling how many parallel streams you are using in the system, how much bandwidth the system is using, and how we are packetizing information. Okay? This is decided by this pipeline, which is analyzing the context where we are operating. So it's understanding how these spikes appear and how they propagate through the system over time and over the stack. Is also trying, like, making some prediction decisions in a specialized way. It's a kind of neural network that is called quantile network, which is essentially trying to predict the distribution of delay over time, and so we can make decisions about that are informed by resiliency of a system. And this is actually very interesting in a way, as we can show, you can see it, you cannot see much this, but what happens is that overall, when we consider all of this, we are using a lot less resources to support these kind of systems, which means we can fit more rovers, we can fit more users, we can actually make this happen in a viable way. Hopefully soon, when we put this together with our AI models, we can actually jointly control how we communicate and how we process. And then the next step is to build this at the infrastructure level. And that is, I think, what needs to happen to fully control this kind of systems. Again, it's a lot more delicate and complex than people think in general. The question is, if you think about a swarm of drones, can you have a different drones perform different tasks, right? And still, so this is the kind of logic that actually would make this relatively easier in a way, because you can actually have in one place the whole logic, right, and compress the information as it travels from the drones. So the way I see it, and actually the system that we're trying to build a little more practically, is that you can think of drones as sensors, and that's it, and then you are controlling the sensors. And that's the way that the model is going to look at it from a point of view of how you move and how you acquire information. For instance, some drones may have LiDAR, some drones may not have LiDAR, some drones may be more capable, some drones may be less capable. I think it's relatively easy if you have a central point of control to build the control logic that actually makes this happen. The system that we're building now has a micro drone that has only RGB image, so plain image. And then we have a rover that has a LiDAR and a binocular camera. And so the rover will use the micro drone essentially to explore some of the, like building some portions of a 3D map. And then the 3D map that is stored at the rover will be used to localize the small drone. And so we can build this kind of logics when you think about like a full system.
Another question I have is,
Yeah, so the question is, if you have many cars on the road, can you have some cars essentially processing information and communicating between them? So that's something that is happening in a way, at least academically, let's say. You have protocols for communications between vehicles, so vehicle-to-vehicle communications and vehicle-to-infrastructure communications. And there are ideas like platooning, of course, where you have the first vehicles that are taking most of the load, and then the rest of the vehicles are mostly controlling their position with respect to the leaders. So that has been investigated for quite some time. One aspect of this, which is maybe a little bit less evolved, is the idea that, so the cars have sensors, right, but they have a very partial view. So you can actually, edge computing is one way of aggregating this information. For instance, if you transfer the data or some data from the vehicles to the edge, you can build 3D maps. This is used to update the 3D maps that the vehicles use, for instance, to self-localize. So in vehicular autonomy, GPS is one resource, right? But it's not very accurate. And sometimes, in some settings, it's dramatically inaccurate. Like as soon as you have buildings around you, things get like really inaccurate, right? You don't have a lot of precision, so you need to localize yourself based on the sensors. The way it's done is that you can actually use either a full 3D map or some landmarks in the whatever is in front of you, but then you need a good notion of how the environment is structured, and that needs to be updated quite frequently. So that's something that is done at the edge. Yeah, I mean, you can be as complicated as you want, but people think about this as, you want these vehicles to be operational in any environment. But the sad truth, by the way, is that I had an interesting interaction about this with the Department of Transportation. So if you think about autonomous vehicles, they're mostly designed for urban environments. And the thing is that urban environments is where autonomy is mostly profitable, because of course you have the highest density of people. It's also like the most complex in a way from a semantic perspective. So we just responded to a call for proposals from the Department of Transportation for rural environments. And those are environments that are typically a lot simpler from a semantic perspective, but you have a lot more unknowns. Like for instance, you don't know what the road conditions are 10 miles from now, and if you realize 10 miles from now you need to drive back 100 miles, right? And so the problem is how you integrate sensors or imaging from different assets, and you build routes dynamically based on events that may happen and that nobody noticed so far. And so you need to integrate different layers of airborne and satellite and the cars themselves. But it's interesting when you think about like general deployment of this, how difficult it is, because there are completely different environments. And the technologies that we have right now, you need to rebuild them for every city, right? Because the traffic signs are a little different, everything is a little different, and then you need to retrain. And this is true for most AI, like sadly. Again, interacting with some companies, I remember there were some solutions that, algorithms for submarine autonomous vehicles that work in the Pacific, but didn't work in the Atlantic. And then we needed to retrain the whole thing. And well, but like some examples are simpler than others, right? Because if I think about, again, if we go back to these examples about autonomous navigation, right? And you go back to, and you say, okay, I want to navigate in one city, and then I need to build navigation logics for another city, and then things are different. So I need to expand my training set. But there are a lot of times events that are very rare and that do not appear very often in the training set, and that's the problem. And again, it's also hard to make these kind of algorithms capable of handling so many different conditions in terms of illumination, weather conditions. Like this rural autonomous vehicles for rural environment call was very interesting. At some point, we started reasoning. We had on board the University of Hawaii, University of Alaska, University of Riverside, and we're thinking like these are really different environments. Like one is, island hopping with an airborne device, and Alaska and rural Alabama are fairly different environment in terms of how people move, but in terms of the raw operations of a vehicle, so how you build things that work, it's a very big question. Yeah, so again, projections are projections. My experience is that these kind of algorithms altogether would require quite a jump. The question is about why can't we, when we think about autonomy, we should think about autonomous, being isolated in a way and fully autonomous, right? So, I can agree, but you can take like that has been actually the way it has been done for many different reasons. It's, for instance, in the context of cars, it's just safety and resiliency of a system. It's very hard to think about a fully reliable system that is relying on something else that may appear, disappear, may be available, may not be available. That's a huge problem. And as a matter of fact, I wouldn't put this kind of, maybe a full adaptation in a car or in a fighter jet. But there are other systems that are definitely not going to be capable of this kind of logic, no matter what you do. And that even if you take, the latest NVIDIA releases, they cannot do much more than, even projecting them, I don't think they can fully support this kind of reasoning, not because they're not capable, but even just because of energy, right? When you put batteries on something like that, the battery are actually the biggest payload of a drone. My hexacopter is like this, but it has 2 batteries like this. It lasts 30 minutes. If I put a GPU, it lasts 10, right? So a micro drone is going to be worse than this. So there are, like, the 5G vision, by the way, is to integrate computing into the infrastructure. We don't have it fully because 5G has been coming like piece by piece, right? Mostly starting from the communication, which is, what we have right now, but the physical layer. But the vision for those kind of systems is the integration of a pipeline. And there are a lot of systems that are moving in that direction. I had conversations with companies doing ultrasound, and they were saying, okay, my ultrasound has, it's a machine like this because it has AI on it and has GPUs, and we need to connect it. I say, Marco, can we build a handheld ultrasound, and then we connect it to a server? And that's one example, because you want to put AI somewhere else, like for many different reasons. And that's a system that we can build, and we can expand capabilities. For instance, the kind of sensors data that you analyze, how you transform them, you can enhance capabilities. But in general, swarm technologies, for instance, are inherently connected. Vehicles are going to be connected, and for a simple reason that your field of vision is often abstracted, and you can be a lot more efficient if you share data in a way, or if you make joint decisions. And I can agree that even an isolated vehicle, autonomous vehicle, can be better than most drivers, and we can be happy with it, but not all the time. And that's the problem. And when you go into my world, which is made of smaller devices and still big autonomy, that's where the challenge is in many ways. So if you ask Waymo, what is your problem? Is computing, is energy? No. The problem is data. I want as much data as possible because I want to train my algorithms for every possible case, right? That's the problem. I want to put, my a cabinet and in a truck. I'm going to be happy with that.
That sounds a little bit like the original AI, which was to create a decision tree where we had every possible decision, and we figured out in advance what to do. That's not the way to solve the problem.
Well, yeah, but the problem they have is that if they fail once, then the city will take away their license to operate, and then this happened, right, with the first responders, right? The vehicles didn't interact well with first responders. They blocked the road, and the first responders couldn't go through. City wasn't very happy about this, and then but again, there are many different problems to me, different layers.
All right, first of all, thank you for the fascinating talk. So I was wondering that operating in a hostile environment, how would that sort of impact your design? Does that impose more constraints, restrictions, or more kind of autonomy?
What kind of hostility are you thinking about?
Like jamming of radios?
Academia kind of hostile?
Well, I guess it's real world, right? There are a lot of jamming of radio signals these days, right?
Yeah, so jamming of signals, of course, is a problem, right? In defense settings, jamming is definitely one of the things that is happening, like in Ukraine, like jamming GPS, of course, jamming of like radio frequencies. So one thing that I can tell you is that if you transmit 1 kilobyte instead of 800, you tend to be like more resilient because you can transmit with more energy, or you can transmit a shorter time, or you can channel hop. like a hostile cannot jam the whole spectrum all the time, right? That's the thing. But definitely, these kind of algorithms, I show you like very briefly, but you can build them with a fallback option that is maybe more limited functionalities, but is fully on board, right? So maybe you don't have all the fancy 3D mapping, all the things, but you can still navigate somehow, right? That's something that can be done.
With anything of consequence, don't you want a live stream of video or something that is human, processable, or right? So doesn't that makes it that you're gonna have that stream anyways?
Yeah, so it depends on the application, right? So if you do want to have an operator fully processing the data, or being able to record the data for, I don't know, you are a city and you want to give a ticket, then you need a full image, right?
Yeah.
You don't want some tensor compressed tensor representation.
I mean, can you get both by having image compression that is tuned to what AIs look for, or something like that, that is a general solution to streaming the data, so that you have something that you could log and use for improving the system in a live system?
No. So what we do is essentially tune compression for AI consumption, right? In a way. What I can observe is that typically AI, like this kind of control problems, right? They are very high temporal resolution. So you need to process an image every, like, I don't know, 20 frames per second, 10 frames per second. Every now and then you can send an image which is compressed to recover the full image, right? For instance, that's something you can do. Or you can send portions of images that are of interest. That's something you can do even with this. I send you a compressed representation, you detect the object, you send back the location, I send you back the portions, right? That's something you can do. There are other, maybe a little more wild guesses that I have, is that you can build these kind of representations that are specialized for human completed tasks. For instance, instead of human enjoyment, you have somebody who is detecting objects, and you probably don't need a full resolution image to do this. So my guess is that a remote operator should actually have a specific representation which is tuned for the specific task, and you don't need the full sensor stream depending on the task. So these algorithms could be trained, this way of training the algorithms could be used for human task specific consumption, not enjoyment, right? Consumption. And you can put as many parameters that you want on it, like how tired the operator is, how complex the task is, what task it is. And the problem is building data sets for these kind of things.
Would bottleneck data, if you log that, would that even be useful for training future iteration of a model?
You can build that in different ways. What you need at the beginning of this whole process is a functional pipeline. And then you can train these algorithms to mimic what's happening in that pipeline. So
it might end up with things that you can't really use on the next model if it's so tied into the previous model.
So what we have seen is that many of these representations actually generalize to some different tasks. Like if we use the same compressed tensors, you can actually support multiple tasks, like segmentation, classification. The performance curve is different, but you can build like slightly more general compression techniques. If you want to be like really high performance in terms of compression, you need to be specific on the task, like navigation. Then that factors in the kind of resolution that the controller will need to make decisions, and that's a very a very specific kind of task. So what you do is you build the system first with no compression. You have a full pipeline, and then you train these compression models to mimic the functionalities of original model. If you have an operator, you need to have operators that perform the task and essentially build the feedback to the compressor in a way.
So Dr. Alvarado, we'd really like to thank you very much for joining us tonight.
Thank you.
Awesome.
I hope
Thank you
you
very much.
enjoyed.